Hi guys. So today we are going to look at chemical equilibrium. If you're using the Brown-LeMay textbook to subsidize what we're talking about here, that is going to be chapter 15. And we see here on our first screen, we have our fun fact of the lecture. A jumbo jet carries enough fuel to drive an average car around the world 50 times. And I've chosen this fun fact for this one because, as we know, fuel is a combustion reaction. And as we go down here to our first slide, we are going to be looking at chemical reactions for the entirety of this unit. And 99.9% of chemical reactions are reversible. That very few percent that are not reversible are combustion reactions. So you can picture if you put some lighter fluid, don't do this at home, please. If you put some lighter fluid on something and you strike a match and throw it on top of there, whatever it was that you were burning, let's say logs in a fire pit, that's going to turn into carbon dioxide and water. We can't turn that carbon dioxide and water back into those logs, right? So combustion reactions are not reversible, but most of all the other reactions that occur are reversible. And here we see just very simply a forward reaction. Here we have our reactants going to products, and we're showing the reverse of that would be our products turning into reactants and our reactants turning into products. We remember this from Chem 1. So when we start our forward reaction, only A and B is present, right? And as the reaction goes towards making products, there is a buildup of products, and in this example, C and D. So as it's going along and making products, it's going to slow down. The forward reaction slows down because we're building up products and we're reducing our reactants. So people who had me for Chem 1 know one of my favorite stoichiometry examples is making s'mores, right? So if our reactants are all these graham crackers and marshmallows and chocolate and we're making s'mores, as we run out of those ingredients and we have tons and tons of s'mores sitting around us, sounds like a lot of fun, right? We're going to slow down production because we're going to have enough s'mores and we don't, and we're running out of those ingredients. Well, in a chemical reaction, as we build up product, it slows down. What we're using is our reactants, and the rates start to equal out the forward and the reverse. And when that flow equals out, that's how we get that double arrow there. So you can see that double arrow is showing us that our reactions are flowing forward just as much as they are backwards. So let's look at this with some data. Give us some concrete things to look at here. So we have two different graphs, and we're looking at this chemical formula right here. We have N2O4 in gas form is breaking down into nitrogen dioxide and creating 2 moles of that. And so we see here we're talking about concentration. And when we're talking about concentration in chemistry, what are we usually talking about? We're usually talking about molarity, right? Very often concentration is looking at the molarity. So here we have concentration. And when we start at time 0, we have very little of our product. We actually have 0 of our product because the reaction hasn't occurred yet. And we should have 100% of our reactants or ingredients because we haven't used any of them up yet. And so once we mix these two things together at time 0 and time moves along, we see that our ingredients get used up and our products are produced. And at a certain point here, okay, we see that they're plateauing. They are not equal. A lot of people like to think, because we're talking about chemical equilibrium, that concentration needs to be equal. Concentration is not going to be equal at chemical equilibrium. It's just going to be constant. We're no longer going to use up our reactants, and we're not going to produce any more product. The concentration is going to stay constant, but they don't need to be equal. So why use the word equilibrium? Well, that refers to rate. Over here, we're talking about rate. And so here we see at time 0, again, we have 0 amount of our product. And here we have 100% of our reactants. And as we move forward through time, at a certain point, the rate in which they are being produced or used up becomes equal. So when we talk about chemical equilibrium, we're talking about the moment that the rate of products being produced and reactants being used becoming equal. So rates are equal, and we see right here. And so this line is the point in which equilibrium is achieved, meaning the rates are equal. And we see over here when we look at concentration that equilibrium for concentration means that our concentrations of products and reactants are now going to be constant, but it does not mean that they're going to be equal. That's a huge, huge point for us to understand when we're talking about chemical equilibrium. Okay, so as we move forward, we're going to talk about the equilibrium constant. You want to keep in mind that equilibrium constant means that the rate is equal for reactants being used up and products being produced, but the concentrations are not equal. They are constant. So got to keep that in mind. Okay, so our equilibrium constant is a formula here. We call it the law of mass action. So here we have a chemical equation, and we've replaced the coefficients with letters so that we can see how they fit into this formula. So the law of mass action is represented by the equilibrium constant expression. Remember that when we use the word expression, we are not using numbers. We're not doing calculations. When we write an expression, that means we're showing their relationships with one another. So here we see the equilibrium constant is written with a K. The reason it's written with a K is that this constant was developed by German scientists, and they spell the word constant in German with a K. So that's why we have a K there instead of a C. And it is a capital K. Lowercase k's mean different things in chemistry. So equilibrium constant is a capital K. So here we see basically, let me get my stylus out here and try and write some notes. So basically what we're seeing is that we have the concentration. Remember that those brackets mean concentration, okay? And it is the concentration of the products multiplied, not added, divided by the concentration of the reactants. So products are on the top and reactants are on the bottom. And we see here that we have turned the coefficients into exponents. So whatever the concentration of C is, we're making the coefficient its exponent, and the concentration of whatever D is, its coefficient M is now its exponent. And so this is the formula to calculate the equilibrium constant. So let's use this equilibrium constant with the equation that we were just looking at in that graph 2 slides back. So our formula, please have patience with me, I'm using a tablet to write and it is not easy. So our formula 2 slides ago with the graph was this guy. Okay. So to put this into our equilibrium constant, we're going to have the concentration of our product with the coefficient as the exponent divided by the concentration of our reactants, and the coefficient's 1, so we don't have anything to do there. Let's say at equilibrium, we know it's at equilibrium because we have these lines here showing us that it's flowing back and forth at an equal rate. Let's say that the concentration of our product is 4 molar. I'm choosing numbers that are easy just for us to see the concepts, not worry about the math. And let's say at equilibrium, remember rates are equal, the concentration of this guy is 2 molar. So that means that the concentrations are constant but not equal, but the rate that product is being produced and there's a flow back to ingredients is equal. So if we throw these numbers in here, we have 4 squared divided by 2, which means our equilibrium constant is 8. Note that there's no units. Oh my gosh, so hard to write in this thing. Like serial killer's handwriting. No units for equilibrium constant. That's good, right? Makes it easy. Okay, so what does this K mean? I mean, that 8. So if K is greater than 1, then that means the concentration of products is greater than the concentration of reactants. Oops, forgot an E. Reactants. If K is less than 1, then we have the reverse, and it means that our reactants, our concentration reactants, are going to be greater than products at equilibrium. Okay? All right, moving forward. Okay, and so let's look at a more elaborate example here. So we have 2 reactants and we have 2 products, and we see here when we put it into our equilibrium expression, what we have with our products up top, coefficients as exponents, reactants on the bottom, coefficients as exponents. Now, this is an expression, so we have no numbers. They haven't given us concentrations of any of these guys. They haven't given us the equilibrium constant. So this is just an expression. We're just laying out the formula. Now, keep in mind, you can also be given the equilibrium constant and some of the concentrations and need to figure out one of the concentrations, right? We can do this in the reverse direction algebra, sneaky algebra. All right, so let's look at some different scenarios here with this expression. So expressions for a reaction that's written in reverse is just going to be the reciprocal, right? So take a look. Here we have this equation, and we've written it in the reverse. So here we have K equals 10. So remember that our equilibrium constant is product over reactant. Oh my gosh, spelling it wrong again. Okay, so if we come down here and we reverse this, our reactant is now our product, and our product is now our reactant. So if we have 10, then that's basically the same as writing 10 over 1. So if we're reversing this and heading in the opposite direction, then we're just reversing that, and we're going to have 1 over 10 or 0.1. So when we flip something, we're flipping that fraction or ratio. So just remember that if you have a whole number, it's really just over 1. All right, let's look at a different scenario with an equilibrium expression. Notice we're not putting in the concentrations there. We're just using what we know the equilibrium constant is and seeing how changing our formulas around change our equilibrium constant. Okay, so our next one is if we multiply our coefficients, then we're going to change our equilibrium constant by that same amount. So here we have our example again. The equilibrium constant is still 10, but let's say we need to double everything. Notice the relationship between our first equation and our second equation is everything is multiplied by 2. And so that means that we are going to change that exponent by 2, right? Because we're changing our coefficients by 2. That means that it's exponent. So some people like to go, oh, it's times 2, so that means 10 times 2. It does not. Remember, coefficients become exponents. So we have to turn that times 2 into an exponent. So let's say if we were to take this equation and multiply everything by 3, then we would do 10 to the third. That 3 would become an exponent, and our equilibrium constant would be 1,000. So we would have a lot more product than we do reactants, right? Because K would be so much more than greater than 1. All right, let's take a look at a chart here. Let's break down what's going on in this chart. So first off, we read up here, it's initial and equilibrium concentrations of N2O4 and NO2. So we're still talking about that same equation that was back in the graphs where we first started talking about equilibrium constant at 100 degrees Celsius. So the temperature is not changing. And we look here and we see initial concentration of our reactants, initial concentration of our products, and we see our differences here, okay? And at equilibrium, we see concentrations here, and they are all different numbers, but when we look at the equilibrium constant, we see that they are basically the same number. So what we're saying here, what this chart, or table, sorry, not a chart, what this table is saying is that it does not matter what the concentrations are, the equilibrium constant will be the same. The equilibrium constant is only going to change with a change in temperature. Remember Lechantiers' principle back from Chem 1, flashback, right? That temperature is energy. And so it depends if we have an exothermic or endothermic equation. We'll talk, or reaction, we'll talk more about that later. But we're going to treat energy either as a reactant or a product, depending if it's endothermic or exothermic. And that is going to change our equilibrium expression. More on that later. But anyway, concentration does not change the equilibrium constant. All right, so something a little different. Equilibrium expressions with pressure. Very important. If we're talking about pressure, we're talking about things that are in gas phase only. Okay, I'm going to highlight that. Doop. I don't know if that's helpful or not. But anyway, for reactions that occur in the gas phase only. So here you see we have a chemical equation. Everything is in gas phase. And so we can put it into our equilibrium expression. We can include everything here. We're still putting the coefficients as the exponents. We still have products on top and reactants on the bottom. What are some differences here from our earlier equilibrium expressions? Well, first off, we have Kp for pressure instead of just a K or Kc for concentration. And we do not have brackets anymore. We have parentheses because we are now talking about pressure instead of molarity or concentration, because we are in a gas. And we still have coefficients as exponents. So instead of concentration, we're going to put the pressure value for these gases. So, let's go back for a second. So let's say, just for the sake of argument, that SO2 is a solid at room temperature. Okay, it is not, it's a gas at room temperature, but let's pretend that it's a solid. If it's a solid at room temperature, then we just take it out of this formula. We're not even going to include it. So if we're figuring out the equilibrium expression with pressure, a solid isn't even in there. Let's say that SO3 is a liquid at room temperature, okay? Then this guy, not even here in this formula. What would we put here? We would put a 1, right? That would just become a 1, and whatever the pressure of oxygen is would be under 1, and that would be our equilibrium expression with pressure, our Kp. All right, so we would just put a 1 there. So if something is not a gas, it is not going into a calculation to figure out Kp. Make sure you're paying attention to those phases of matter there. So heterogeneous equilibrium is heterogeneous. Remember, heterogeneous means that we have different things involved in the same space here. So it is equilibrium that involves more than one phase. And we can see here that we've got a solid, and a gas. So the only thing that we can use to figure out our Kp here is those should not be brackets. That should be parentheses because it's a gas. So it should just be the pressure. The Kp would be the pressure of the carbon dioxide gas. The position of a heterogeneous equilibrium does not depend on the amounts of pure solids or liquids present. So we can only use, for K, we can only use gas and, what's the other guy? aqueous. We can only use aqueous solutions. We cannot use solids or liquids to figure out our equilibrium constants. All right, Q. We're going to take a pause here and make a new video starting to talk about Q.